Okay, so today for the upcoming Shock 2 special experiment, what we're going to be talking about is we're going to be talking about compressible flows. And so what that means is that we have flows whose Mach number is now starting to be reasonably sized compared to the speed of sound in that flow. And it also means that changes in density in our flows are going to be important. All right, so let's think about how do we actually define these classes of flows. And the first thing that we consider here is we define the idea of the Mach number. And so we define our Mach number, m is equal to my flow velocity u over my speed of sound a. And if I define my flow velocity u over my speed of sound a, effectively what I'm defining here is the rate of fluid motion in my flow, and then the rate of pressure distribution or pressure information in my flow. And for the case of this class, we're going to define A as square root of gamma RT. And so as my Mach number increases, my flow velocity increases with respect to my speed of sound. And so let's consider some regions of this flow. So for Mach numbers, these are approximate numbers. For Mach numbers less than 0.3, so low speed flows oftentimes will consider this region to be incompressible, or at least incompressible assumption allows to have useful results. And then let's consider our region from From 0.3 to 0.8, we'll refer to this as being subsonic. And so in this subsonic region, we do have compressibility effects, right? Between Mach number 0.3 and between Mach number 0.8, we're going to have compressible effects, but we're not going to have any shocks. We're not necessarily going to have any discontinuities. As we approach a Mach number of 1, so let's say that our Mach number is between 0.8 and 1.2. What we enter here is we refer to this as the transonic region. And within this transonic region, you can have flows with and without shocks, right? And so in this case, we are close enough to the supersonic region that depending on your flow geometry, depending on your pressure distribution, you can have regions within your mean flow that do achieve sonic conditions. And so in this transonic regime, you actually have to be careful with these effects, and it's actually reasonably difficult to do analysis in this transonic regime because of that geometric effect. So if we have our Mach number go, let's say above 1.2, and we'll say under 5-ish is a good number. This is now the supersonic regime. And in the supersonic regime, now I have compressible flow with shocks and with discontinuities, right? Now I have a flow velocity or fluid velocity that is faster than my speed of sound, or faster than the rate at which pressure information can communicate through my fluid. We can even go one step further. We can go if Mach number is greater than 5. We enter the hypersonic regime. And in the case of the hypersonic regime, now we start to have even more problems. We have issues with real gas effects, right? We can no longer consider this being an ideal gas. Also, we can have issues with flow reactivity. We can reach extremely high pressures. And so chemical reactions, these things now matter within my flow as I enter that hypersonic regime. And so, in the case of the Mach number, again, we can think about it as the rate of fluid motion versus the rate of pressure distribution or pressure information. And for the purposes of our lab or our discussion, we are going to exist. Will exist in this supersonic regime. So, what does it mean, right? This is the classic cartoon diagram of what does it mean to actually have a supersonic flow. So, imagine I have this blue dot, and this blue dot is a beeper, and periodically it beeps. And when it beeps, these red sound waves propagate out from my beeper, right? And so, if I have a velocity of 0 meters a second, I beep, and my sound waves just propagate nicely radially outward from my dot as if they are ripples in a pond. So let's increase my velocity. So in this case, my flow velocity u is less than my speed of sound a, and my Mach number is less than 1. What this means is as my blue dot is traveling and emitting these beeps, all right, you will see that I have a larger spacing between my beeps, or between my sound waves behind, and I have a shorter spacing in front, right? That's because my overall propagation with respect to my beeper, in the case of the front of my sound waves, is going to be the speed of sound minus the velocity of my beeper, and behind it, it's going to be the speed of sound plus the velocity of my beeper. So I'm going to get different spacing between my sound waves here, and different spacing between my sound waves here. You guys are familiar with this when an ambulance passes past you on the street. This is the Doppler effect, causing you to have lower frequency sounds when something's coming away, and higher frequency sounds when it's approaching. So let's consider now the case where my flow velocity is equal to my speed of sound. Right? If my flow velocity is equal to my speed of sound, I still get large differences in my sound waves behind my beeper, right? I'm traveling. The effective distance in those is going to be the speed of sound plus the velocity of my beeper, which is u. However, at the front, notice that all of these sound waves are simply stacking up upon each other. Right? My beeper is moving at the exact same rate in which these sound waves are going to propagate. And so now let's consider what happens when my beeper is then moving faster than the speed of sound. So now my beeper is moving faster than the speed of sound, which means that it's going to emit its sound waves. And those sound waves are then going to trail behind the beeper. The beeper is able to move faster than the propagation of that pressure. So what I'll see is my dot. Will begin forming behind my beeper. And what I have in output is what referred to as a Mach cone behind my beeper. And this actually has a defined shape and a defined angle. But what I'm seeing here is that now my object is moving so quickly in the flow that ahead of that object, I don't have pressure information. I don't have any feedback, right? In this case, my fluid particle is here, right? In the case of where I'm subsonic, right? If I have a fluid particle here, in this subsonic case, my fluid particle has a buildup of pressure or a pressure gradient, right? That allows it to react to this object. Right? It can see this information, right? My pressure information or my speed of sound is propagating faster. So this piece of fluid knows that the beeper is coming, or it knows that the object's coming in the flow. In the case of my supersonic flow, my fluid packet now has no idea. Right? Fluid packet doesn't know that this object is coming, right? You wouldn't be able to hear this object as it's traveling towards you at a supersonic speed. However, when it passes, you'll definitely hear it. We'll talk about that. So let's illustrate this another way. So let's say that my Mach number is less than 1, and I have some object, and this object exists in a flow. Right? I will get a pressure gradient that forms on the surface of this object thanks to this object being within my flow. Right? We talked about aerodynamic forces, we talked about how they form about airflow, we talked about how those relate to a summation of pressure gradient forces. So if I take this object and I stick it in the flow, what we'll see is my flow move around this object. And because my Mach number is less than 1, the flow that is approaching my object reaches a transmittable pressure gradient on the surface. And so my fluid here, right, experienced some my fluid here experiences some pressure gradient. And that pressure gradient is able to then turn the flow around my object. Right? Because this pressure information is able to propagate faster than my fluid motion or faster than the motion of my object. So, what happens now in the case of my Mach number being greater? my Mach number being greater than 1. Here is my object. Right? And now I have a supersonic flow coming into this object. And as we stated earlier, in the supersonic case, right, just pressure information is not able to propagate faster than the speed of sound, so thus it's not able to propagate in this upstream flow. And so this flow here no longer has the information about this object. No more information about this object, and thus that flow doesn't know to turn around the object. Right? Is that physically possible? No, the air needs to be turned around the object. And the way that this gets set up is in the flow, what we're going to refer to, at least in this class, as being a discontinuity form. And so in this case, what you have is a shock. And what this shock is doing, or within this shock, is we're taking this flow, and we're taking it from a flow that is greater on this side, and through this continuity based on conservation of energy, mass, and momentum, what we end up then with is a subsonic flow on the other side of this shock. And now if I have a subsonic flow on the other side of the shock, what that allows me to do is establish a pressure gradient and actually turn my flow around the object. So a couple of different ways to think about how does this form, right? What happens when we have these supersonic flows? And so what are we actually going to do with this, right? How are we going to talk about this mathematically? As we talk about these flows, and we talk about this idea of a discontinuity, or we talk about this idea of a shock, the thing that we're going to be considering is conservation of mass, momentum, and energy. Conservation of mass, momentum, and energy are what dictate this behavior and actually allow us to make some calculations based on ultimately what is a extreme buildup of these pressure forces or these pressure waves that eventually condense down into, again, what we're considering to be basically infinitesimal discontinuity. In reality, is there some thickness? Is there some process in there? Yes, but in this relatively simplified case, what we can consider is, again, the discontinuity between a supersonic state and a subsonic state. So, let's start off in MECOP, as always, with some assumptions. So, first what we're going to assume is, first of all, we're going to assume for our analysis that we're conducting these experiments, we're going to conduct our experiments at moderate temperatures. So basically think about that as room temperature. And if we do this, what we can assume is we can assume a calorically perfect gas. And what I mean by saying I have a calorically perfect gas is I mean that my value of gamma is constant. And so gamma is our ratio of specific heat. It's Cp over Cv. In this case, we're assuming that gamma is a constant value. All right, so we said that we're existing in this supersonic regime, and in fact, we're existing sort of at the lower end of our supersonic regime. I don't think we see anything above Mach number 2 in this lab. And that allows us to make this calorically perfect gas assumption. The next thing we're going to assume is that this process is adiabatic. And what that means is that the energy before and after my shockwave is the same. And so now let's begin formulating the idea of how do I understand my gas properties ahead of the shock and after the shock. So, let's consider my fluid flow ahead of the shock. Right? Ahead of the shock, my flow has some velocity u, it has some density rho, right? It has some temperature T. Behind the shock, I have some velocity rho, I have some velocity u, and I have some temperature T. And what I'd like to do is I'd like to take the total temperature, total energy, total density ahead of my shock and write that as a value, right? A total temperature, total density, total energy. Because based on my adiabatic assumption and my assumption of a calorically perfect gas, that would allow me to relate the state ahead of my shock to the state after my shock. And so the way that we're going to define these total temperatures, total pressures, right? So we'll call these, total quantities. The way that we define these is we assume that if I have that given state of flow, right? If I have my flow ahead of the shock at state 1, or my flow behind the shock at state 2, I can then isentropically decelerate that flow to rest. All right, so imagine I was able to decelerate that flow in a reversible process. And so, if you can, isentropically decelerate flow if you can isentropically decelerate your flow to a velocity of 0, or 0 velocity, right? I can then use the isentropic relations to relate those two states, right? So my isentropic relations say that P2 over P1 is equal to T2 over T1 to the gamma over gamma minus 1, which is equal to rho 2 over rho 1 gamma, right? I can now take my initial state, right? My state at a velocity of something, my density of something, my temperature of something. I can decelerate that to 0, use my isentropic relations, and thus I can define my total properties. All right? So I can define total temperature. T0 over T. Right? So T0 is my total temperature, and that's going to be 1 plus gamma minus 1 over 2 m squared. I can define P0 over P is 1 plus gamma minus 1 over 2 m squared gamma minus 1. And I can define my total density, rho 0 over rho is equal to 1 plus gamma minus 1 over 2 m squared 1 minus gamma minus 1. And on Blackboard, we have put a snippet from Compressible Flows by John D. Anderson, who also wrote the snippets for the aerodynamic stuff. And the majority of this, in fact, a much more detailed derivation of these quantities, exists in that document. But what this allows us to do is, writing it in this fashion, allows us to write these three key quantities of interest as a function of Mach number and my ratio of specific heats, gamma. And now what this allows us to do, it allows us to relate the state ahead of my shock and the state after my shock. Right? If I consider that there's no energy added or subtracted to my flow, aka my adiabatic assumption, what I can assume then is that my value for T0, my value for P0, and my value for rho 0 now are all constant. Okay? And if I know that my values for T0, P0, and rho 0 are now all constant, then I can use that information to set up a system of equations and solve them for my states ahead of my shock and after my shock. And so let's define the idea of a normal shock. And so we'll consider a normal shock wave. As a shock wave that's traveling in 1D, and we can also assume an infinite medium in that 1D. It's traveling between a state 1 and state 2. And so at my state 1, I can define a value for P1. I can define a value for T1. I can define a value for rho 1, define a value for U1, and I know that my M1 exists, which is greater than 1. Right? Then I have a state 2. And in my state 2, I can define a P2, a T2, a rho 2, a U2, and then an M, which will be less than 1. And now, if I take my state 1 and state 2, I consider my total temperatures, and I look at conservation of energy, or apply conservation of energy, mass, and momentum to what I assume is a one-dimensional adiabatic process, I can now relate my equations of state between state 1 and state 2. Again, through this, my values of my total temperatures. And so now I can start having some comparisons between state 1 and state 2. I could write P2 over P1 is equal to 1 plus 2 gamma over gamma plus 1 and 1 squared plus 1. I can write my ratio of my densities, rho 2 over rho 1 is equal to U1 over U2, right? If I assume I have a constant property state here, a constant property state here, and I'm assuming only motion in one dimension based on conservation of momentum, right? My density should be the same ratio as my ratio of velocities. And gamma plus 1 and 1 squared over 2 plus gamma minus 1 and 1 squared. And then I can also write my ratio of my temperatures between state 1 and state 2. My ratio of temperatures will simply be P1 or P2 times P1 multiplied by rho 1, rho 2. So again, now I can relate all of my properties ahead and after the ratios of my properties. It's simply a function of my Mach number and my ratio of specific heats, gamma. And so with a normal shock, we have some expectations, right? My first expectation is that M1 has to be greater than 1, right? For us to have this discontinuity, for us to have shocks in our flow needs to be supersonic. So we expect that our M1 is greater than 1. We also expect that M2 is less than 1. All right? And if we make this assumption, we can say that my differences in pressure, right? We expect a pressure discontinuity. We expect a larger density ahead of my shock than after my shock, right? We expect a slower velocity. So U2 is less than U1. And we expect that T2 has a much higher temperature than T1. Right? And it's relatively easy to think about this. If we think about, again, we have conservation of energy before and after. Right? If I have a flow here that is supersonic, and then a flow behind my shock that is subsonic, that energy has to go somewhere. Right? I have much higher kinetic energy in my flow than here if I was thinking about it just in terms of momentum. And that energy has to go somewhere, and what that results in is, again, higher temperatures, right? Higher pressures for our shock. Okay, so any questions about how we set up this idea of a normal shock? Yes?
Could you explain about total quantities? Because so what the total quantity is like we're taking before the like the state 1, I guess. We're just kind of combining all together to be a total quantity.
What the total quantity is it is a measurement of the easiest way to think about that is think about total temperature, right? There is some kinetic energy in my flow, I have some temperature in my flow. But because I have a flow velocity, there's other energy, right? If I decelerated it, I would see some of that converted to temperature, right? So think about how when we did the wind tunnel experiments, right? We talked about our dynamic pressure, right, where P naught is equal to P1 plus 1/2 rho U squared, right? In the same way, we find our total pressure here, right? We're just defining it in terms of our Mach number. But now that we're at a large velocity, we care about these changes in temperature, we care about these changes in density, and we can write them similarly based on conservation. So these total properties are, if I took a given flow and I isentropically decelerated it or reversibly decelerated it to a zero velocity, now I can define this, right? And so a way to think about that is, again, with the total pressure, same concept as our P0 in the pitot tube experiment and also in our wind tunnel experiment.
So are those just like ambient conditions?
It's not ambient conditions, it would be the conditions in your flow. So if I have a flow at a temperature of T and a Mach number of m, and took that flow isentropically to a velocity of 0 meters a second, my total temperature would then be T0. So just a way to relate the total properties, exactly the same way we did pressure, but now we care about density and temperature as well. Yes?
And when there's a shock, the flow does not go to zero, right?
No, it does not. All right, so let's talk about these shocks. And let's talk about what we actually want to do with these. So why do we care, right? Why do we care about shocks? And in this class, or in this lab, we're going to talk about the idea of a shock tube. And what a shock tube does is it allows us to create these supersonic flows, or allows us to create these shocks in a controllable manner. And why do we want to do this, right? First off, to understand these compressible dynamics. But another reason, and actually a more useful reason, is that we can use these expectations to create specific conditions in the laboratory. And so, if you've ever gotten a chance to tour Caltech, Caltech has a shock tube lab that takes up the entire top floor of a building, and it's used for the evaluation of re-entry vehicles, or re-entry temperatures. And the reason it's used for this is that what I can use is I can take this normal shock, knowing that in my flow I'm going to have a large step change in temperature, or a large step change in pressure, or a large step change in density, and now I can create these properties in the laboratory, right? If I have to study the temperatures and pressures associated with re-entry, that's very difficult. However, I can use this process of a normal shock to see these large jumps in temperature, or these large jumps in pressure, and actually create this as a useful laboratory device. And so, in our discussion of shock tubes, what we're going to be looking at is, can I use my assumptions and these predictions of a normal shock to actually create a reliable experimental device? Can I create shocks in the laboratory repeatedly and with known quantities, right, which will allow me to conduct further experiments? And so, let's consider the concept of a shock tube. So, a shock tube consists of two tubes that have gases at different conditions. So, let's say I have this tube. In this tube, initially, I will have this tube separated by some barrier. So in this case, the center of my tube is divided by a diaphragm. And this can be made of multiple materials. In the case of our lab, we're going to use a thin mylar sheet. In the case of shock tube at Caltech, or large shock tubes, you're considering these made out of actually pieces of aluminum. And we can define the two states, right? This is the initial state we set up this tube. And I'm going to define state 1. Here I'm going to call this state 1. And then I'm going to define this state 4. So pay attention to these numbers. I'm defining that as state 4 for a reason. And what we're going to do is we're going to call these two different sections. So this is going to be called the driven tube. And this will be called the driver tube. And what I'm going to do is I'm going to establish an initial condition where P4 is greater than P1. And so if I plot under my tube my pressure versus distance x, what I will see is my driven tube will be at a P1, and my driver tube will be at. And I've established a discontinuity here, right? Because of this diagram separating my driver tube from my driven tube, I now have a step discontinuity in pressure. So, what I'm going to do next not enough room over there. So, what I'm going to do next is I'm now going to, quote unquote, instantaneously rupture this diaphragm. We're going to assume that it disappears. Right? And what that will do is it will allow for a normal shock. Right? And this discontinuity will then create a normal shock that then travels this way through my tube. And so we'll call this the incident shock. So incident shock. And this incident shock is traveling through my tube into a gas of state 1. Right? Based on our discussion earlier of supersonic flows, does my gas here know the shock is coming? No, it does not. So this remains at state 1. And my normal shock processes gas from state 1 to state 2. So behind my shock, I will refer to this as state 2. Right. I'm not calling this state 4 anymore. State 4, in fact, exists back here. Because what happens in my flow is I have a supersonic condition here, right? I have a supersonic propagation of my incident shock. That incident shock is processing gas from state 1 to state 2. However, behind the shock, now I have subsonic behavior, right? So I have pressure distributions behaving subsonically back here in this region. And so I can define 3 regions. I have region 2, I'll have region 3, and then a region 4. And what separates these? What separates regions 2 and 3 is something known as the contact surface, which I'm going to draw with different. And so what the contact surface is, it is the boundary between the driver gas and the driven gas. All right. In this case, for our shock tube, we're considering our driver gas and our driven gas are the same, and that they actually begin at the same. They actually begin at the same temperature. You can get much broader conditions of your shock tube by actually playing with this idea of having different gases at the discontinuity and also different initial temperatures at that discontinuity. But this contact surface does have an induced flow behind the shock. So this region of pressures 2 and 3 has an induced flow behind the shock, and what we'll do is we'll call this P. Right, so this is my induced flow behind the shock, and this behaves subsonically. And so then my region between 3 and 4 is I have a lower pressure region here, right, created by discontinuity, and it's still initial high pressure region 4 here. Right? Eventually, that high pressure in my region 4 has to expand and reach this equilibrium pressure with the rest of my tube. And so what I end up with is an expansion wave that exists between my states 3 and 4. So let's plot all this in terms of x and see what it looks like. All right, so my state 1, this is pressure, this is x. At state 1, I'm still at P1. I'm still And then my shock processes gas to then state 2. So I have this discontinuity across my shock. Now I'm equal to a pressure P2. And we're going to assume, in this case, that P2 is equal to P3. So then, in the expansion rate, I have a pressure P4, and then a subsonic expansion to this pressure P3. So, a couple of things that are important to note in this case, right? I've ruptured the diaphragm, and what that's done is it's caused me to have an incident shock, right? That incident shock is traveling with some velocity W, and it's traveling with a supersonic velocity with velocity W, right? We're talking about this velocity in reference frame to the tube, right? If I sat on the shock, I would see this basically constant state before and after, but in this case, my shock is moving forward, and it's moving forward at a velocity W. Also note that my shock is driven by a pressure P2 over P1. And so in the shock 2 formula that was handed out in the beginning of class, what you can see is that the majority of these quantities are defined by this ratio P2 over P1, right? As we've defined for the normal shock. And so if you look at our equation 4, right, I can define the Mach number of my incident shock, Ms, based on my pressure ratio P2 over P1 that's driving that shock forward. Right? And note that from my equation 1, I can solve for that P2 over P1 based on my initial conditions of P4 over P1. So I have an incident shock, it's traveling forward. Behind the shock, I have subsonic fluid flow. I have this expansion wave. I have an induced flow velocity UP that is subsonic. And then I have this propagating through my tube supersonically. Okay. So now let's talk about what happens when my shock wave reaches the rear of the tube. So when the shock wave reaches the rear of the tube, right, conservation of mass would then dictate that there is some net velocity going through the end of the tube. Is that possible? No, it is not. So what will then form in my tube is a reflected shock wave. Right, my shock will travel to the end of the tube and then will reflect off the rear of the tube. And travel again supersonically with some velocity WR. And what it will leave behind in its wake is a state 5. And we refer to state 5 as stagnation region because it has to satisfy this condition that mass cannot travel through the rear of the tube, which means that my velocity here my flow velocity here is equal to 0. And my flow is now going to propagate back up through my state 2 and state 3. And there may be a little bit of my state 4 left, but again, this expansion wave is subsonically changing my pressure from state 4 to state 3. And so if I draw this back out, let's consider my pressures. So in this case, I will have a pressure P5, and then I will have a pressure on the other side of P2, which is equal to P3. And note that my pressure behind my shock, right, is higher than the pressure ahead of my shock. Right? And so now my pressure differential between P5 and P2, or P5 and P3, is what's driving my value for WR. Right? Also, you can think about it as the fact that this flow now is going to maintain a zero velocity, and so I'll have to prop it up to a higher pressure, again, for conservation of energy. So now I have P2 is equal to P3. A little bit of expansion, but we're not going all the way up to P4 because this process has been occurring for a little while. So the other thing we have to consider is that we said there's this subsonic flow that's transmitting in, or that's in the tube behind the shock. And so now, my incident shock is, or my reflected shock is flowing through a flow of subsonic velocity UP. And so the first thing we'll have to do in this lab is we're going to be investigating how a shock tube works. So what you're going to do is you're going to establish multiple initial conditions, P4 over P1. And then you're going to measure and then calculate our incident shock Mach number and our reflected shock Mach number and see how they compare to our predicted capabilities, right? We have predicted capabilities coming from the shock tube formulary that we've given you, right? These come from conservation of mass, momentum, and energy as we've set up here. Right? These are the important concepts to understand before you actually use these equations. And so, in order for us to compare these expectations, I have to take some measurements. So the first thing we'll do is we're going to be able to measure our value for MS. So, MS is equal to the incident shock, right? And our incident shock Mach number can be determined by our measured velocity W over the speed of sound in A1. Right? We're defining our Mach number based on the fluid into which our shock is propagating. And so we'll use our measured value of W here and our Mach number A1. We can then calculate our value of MR. And our MR is going to be our velocity WR plus our velocity UP, right? My shock is traveling into a fluid that is subsonically moving with some velocity UP this way. Those velocities are then additive. And that's going to be over my conditions at state 2 in my tube, or A2. And so we'll then use these to compare to our theoretical predictions. So let's think about, how much time do I got? 7 minutes. Let's think about the actual experiment. So for our actual shock tube experiment, we will have a tube. And in this tube, we are going to separate it from the ambient with a mylar diaphragm. And this will allow us to define our two initial states, right? We're going to define our state 1 within our driver tube, and we're going to define our state 4 as being the lag. And what you'll do to establish your P4 over P1 is we're going to use a vacuum pump to then evacuate our shock tube. And what you'll be able to measure then is we'll have a differential pressure gauge. Which is going to allow you to directly measure dP which is going to be P4 minus P1. And then we'll also have a separate static gauge that allows you to measure the ambient conditions P4. And so using this, now what we can do is we can establish an initial P4 over P1. Then what you'll do is we'll take a blade and we will puncture the mylar diaphragm to quote-unquote instantaneously rupture this mylar diaphragm. And what that's going to do is it's going to cause a shock to then travel down my tube. So how are we going to measure the velocity of this shock? And the way we're going to measure that is we're going to, or on the shock tube already, are two sensors. And we're going to call them time of arrival 1 and time of arrival 2. What these sensors are is they're actually piezoelectric pressure transducers. And these piezoelectric pressure transducers compress due to the pressure wave or a change in pressure that causes a small change in their voltage output, and that can then be amplified to measure pressure. However, our pressure transducers have a finite time constant. Right? We talked about time constants in terms of measuring the manometer, in terms of the thermocouple. These piezoelectric pressure transducers also have a time constant on the order of a few milliseconds. However, our shock is actually traveling faster than that, so there isn't enough dwell time, there isn't enough thickness of the actual shock for these sensors to actually read real pressures. And so instead what we're doing is we're looking at the initial spike in their data. That initial spike in their output shows that's when the shock passed over. It's basically an excitation. And so we're referring to them as a time of arrival sensor. I don't know an absolute pressure, or I don't know the pressure of my shock wave from these sensors. However, I do know when they've impacted that device. And so as my shock travels down the tube, I will see a spike from time of arrival 1. I'll see a spike from time of arrival 2. That'll allow me to calculate my velocity W. Then my reflected shock will travel back through the tube, and it will hit time of arrival 2 and time of arrival 1, enabling me to actually calculate these quantities. So, your data will look something like this. E output and time. And we'll call this one time of arrival 1. See something that looks like this. Right, so my first sensor, my shock wave will hit, cause a spike. I'll reflect off the back. I'll hit it again, cause a spike again. And then I'll have time of arrival 2. Will look something like this. So, my incident shock wave comes through the tube, hits time of arrival 1, then hits time of arrival 2, reflects off the rear, hits time of arrival 2 again, then hits time of arrival 1 again. And we can use this to calculate our velocity W, right? Our time of arrival sensors are installed 1 meter apart. And that means that I can use my time differential here. We'll call this TS. And we'll call this TR. To then calculate my values of WS and WR. And if I then calculate my values of WS and WR, I can then calculate my values of MS and MR, which are actually what we're interested in. And then I can plot them in comparison to my theoretical expectations. And how we're going to make that comparison to theoretical expectations is something that we'll talk about more on Wednesday, but this gives you the background to actually take this data. Also note that just like our wind tunnel experiment, this has a substantial quantity of literature available on Blackboard. It's expected that you go through and take a look at that to get a little bit deeper understanding of what I'm talking about here in preparation for the lab. So, see you guys on Wednesday. Note that the sign-up sheets for Shock Tube 3 will go up probably before lab today.